G'day, I'm Terry the Technician, the creator of this podcast.
You know, it's funny. Usually when we talk about modern consumer technology, there is this massive expectation of magic,
Oh,
right?
absolutely. Total magic.
Like you tap a piece of glass and a car just shows up at your house. Or, you speak into a little plastic cylinder on your kitchen counter and groceries arrive the next day.
Yeah, and it's seamless,
Like,
it's beautiful, but it's also a completely sealed shut black box.
exactly, a sealed box.
Yeah.
You aren't really supposed to know what happens when you press that button. You're just supposed to trust all those layers upon layers of software abstractions.
Right, the user interfaces, the operating systems, the cloud APIs.
Yeah, all that stuff that sits between you and the actual physical silicon doing the work.
And I mean, the abstraction is basically the defining characteristic of modern software engineering. We build on top of what others have built, so, we don't have to reinvent the wheel every single time.
Which makes sense, for sure.
It does, but the trade-off is this profound loss of, well, mechanical sympathy.
Mechanical sympathy, I like that.
Yeah. When a developer writes code today, they're just so far removed from the physical electrons moving across a circuit board. The hardware might as well be imaginary.
Right, it's just treated as this infinite, flawless resource that someone else manages.
Exactly. But today, we're doing the exact opposite.
Yes, we are. We are taking a metaphorical crowbar to that black box. We are prying the lid off and going down to the absolute, unforgiving bare metal of computing.
Stripping away the operating systems, the graphical interfaces, all the safety nets.
Right. We're going to learn how to talk directly to the silicon. And the mission of this deep dive is to map out a step-by-step path for an absolute beginner to actually do this.
Even if you have never touched a circuit board in your life.
Exactly. We are exploring how to start programming modern ARM Cortex-M microcontrollers using this radically lean, interactive operating system called Mecrisp-Stellaris.
It's just a fantastic ecosystem. And to guide us, we're unpacking a really fascinating piece of source material today.
Yeah, and it's important to note, this isn't some dry corporate manual pushed out by, a massive tech conglomerate's marketing department.
No, not at all.
We are diving into the Mecrisp-Stellaris Unofficial UserDoc. It is this massive living document, well over 100 pages, and it was created entirely by one person, Terry Porter.
Terry Porter, yeah.
Yeah.
He's a retired Australian electronics technician, right?
Right, with 47 years of industry experience. And honestly, the timeline of his journey is maybe the most inspiring part of this whole deep dive.
Oh, for sure.
Because with nearly a half-century career in electronics, Terry only started learning the Forth programming language, which is what Mecrisp-Stellaris runs on in April of 2014.
Which proves a massive point right out of the gate. It is literally never too late to adopt a radically new computing paradigm.
Yeah.
Because Forth is fundamentally different from the C or Python code that most people are familiar with. And Terry realized that beginner-friendly documentation for this specific language tied to real physical hardware projects, it just didn't exist online around 2015.
So he just built it himself?
He built it himself, leaning on his decades of diagnosing physical circuits.
And that electronics technician background, I mean, it fundamentally changes the tone of the material.
Oh, completely.
Because when you read standard software engineering tutorials today, they sort of exist in the ether.
Right, they talk about instantiating cloud instances or pulling down software libraries. They just assume the hardware works.
Exactly. But Terry's documentation forces you to think in schematics, in timing diagrams, in physical pinouts.
You are looking at the actual metal legs of a microchip.
Yeah, and the sources detail this exact physical setup for one of his hand-soldered projects. I want to paint this picture for you because it totally bridges that gap between hardware and software. He's building a system using a QFN chip.
Right, so for context, QFN stands for quad flat no leads.
No leads, okay.
Yeah, so older microchips usually have little metal legs, the leads sticking out of the sides. They look kind of like a mechanical bug.
Right, the classic computer chip look.
Exactly. And you can easily touch a soldering iron to those legs to attach a wire. But a QFN package has no legs. The electrical connector pads are completely flat on the bottom of this tiny microscopic square of black plastic.
Which means it's notoriously difficult to solder by hand, right?
It's incredibly difficult. These chips are designed for automated factory assembly lines. Where a machine stencils solder paste onto a custom-printed circuit board, places the chip with a robotic vacuum nozzle, and bakes it in a reflow oven.
But Terry is hand soldering this tiny flat chip onto a standard 0.1-inch matrix board.
Basically a blank canvas of copper holes.
Yeah. using 0.5 millimeter wire wrap wire.
We are talking about working under a microscope here,
Routing wires that are essentially the thickness of a human hair.
relying entirely on the surface tension of molten solder to, pull the microscopic pads into contact.
It's wild, and the documentation actually includes these incredible macro photographs of these setups.
Yeah, comparing microscopic chip packages like QFN32, QFN16, and DSBGA.
DSBGA.
Yeah, die-size ball grid array. That is literally a chip the exact size of the silicon die itself, with just microscopic solder balls on the bottom.
Wow. So Terry really grounds the software in physical space by showing you the visceral reality of the silicon you're trying to program.
He does. And the resulting system is just a master class in minimalism. He proves that you can run a complete, fully functional operating system on a single microcontroller that costs roughly 60 cents.
A 60-cent brain.
A 60-cent brain.
Hmm.
And the only external component required to make it function is a single filter capacitor.
Wait, really? Just a 60-cent chip and one capacitor?
That's it. And that single filter capacitor is a great example of the hardware reality you have to embrace here.
How so?
Well, in standard software development, you don't worry about power delivery, right?
No, never.
But when you build from bare silicon, you learn that every time the chip's internal clock ticks, millions of microscopic transistors switch on and off at the exact same time.
Okay.
And that draws a sudden, massive spike of electrical current.
Right, which would cause an issue.
Exactly. Without that tiny filter capacitor acting as a localized energy reservoir, sitting physically close to the chip's power pins, the voltage from your power supply would momentarily sag.
And what happens then?
The chip would instantly crash and reset.
Oh, wow.
Yeah. The software simply cannot function without that physical electrical stability.
That completely changes your perspective. It makes standard software development look like, I don't know, going to a high-end restaurant.
How do you mean?
Well, you sit down, you order from a menu, and a fully formed meal arrives. You don't know where the ingredients came from. You don't know what kind of pan they use. You just consume it.
That's a good analogy, yeah.
But Terry's approach is like walking out into the woods, foraging for your own ingredients, building a fire with friction, and cooking the meal from absolute scratch.
You understand the heat, the smoke, the raw materials down to the molecular level.
Exactly. You know exactly what went into it.
And removing the safety nets of pre-built commercial development boards, it forces that understanding. Like an Arduino, for example, is fantastic for getting beginners started.
Sure, they're super popular.
They are. But an Arduino wraps the bare microcontroller in protective circuitry. It hides the complexity of voltage regulators, external crystal oscillators, USB to serial conversion chips.
It sanitizes the experience.
By bypassing that protective layer and wiring up a bare 60-cent chip yourself, you build a fundamentally deeper comprehension of the electrical realities your code is manipulating.
Because you can't write a line of code without understanding exactly which physical pin is syncing or sourcing current.
Precisely. Which brings us to the software environment actually capable of running on this minimalist setup.
Right, because if you are working with hardware this raw, you need a language that is just as direct and uncompromising.
You do. And the operating system running on that 60-cent chip is Mecrisp-Stellaris.
Which is an embedded Forth environment created by Matthias Kuff, right? Back in June of 2013.
That's the one. And the footprint of this OS is staggering.
Oh, it really is.
The entire operating system fits into just 19 kilobytes of flash memory.
19 kilobytes.
Yeah, and it can run comfortably on as little as 1 kilobyte of RAM.
That is insane. I mean, to contextualize that efficiency for you,
Right.
Let's consider C, which is the undisputed language that runs most of the embedded world.
Right.
If you are writing a standard C program for a microcontroller, just implementing a basic print function, the code required to format a string of text and print it to a screen that alone can easily eat up 20 kilobytes of flash memory.
So a single text formatting function in C takes more space than the entire Mecrisp-Stellaris operating system.
Yes. Its compiler, its interactive user environment, all combined.
That really puts the sheer bloat of modern software into perspective, doesn't it?
It totally does. And the documentation also compares this Forth environment against other popular low-level options like MicroPython, Lua, and Scheme.
Yeah, let's talk about MicroPython because it's incredibly popular right now in the maker movement.
Mostly because it's interactive, right?
Exactly. People love interactivity. But the overhead for MicroPython is massive in comparison to Forth.
Why is that?
Because MicroPython requires a relatively beefy microcontroller with lots of RAM. It relies on a heavy interpreter and a garbage collector.
Oh, right, garbage collection.
Yeah. In Python, you don't manually manage memory. The system just periodically sweeps through the RAM to clean up unused variables.
But wait, in a bare metal hardware environment, couldn't that be a problem?
A huge problem. Imagine you are trying to pulse an LED at highly specific microsecond frequency. If there's a sudden pause in execution because the Python garbage collector decided it was time to clean up memory.
It's going to completely wreck your hardware timing.
Exactly. Forth gives you the interactivity of Python, but with deterministic execution and practically zero overhead.
So let's drill down into that word interactive, because standard C programming workflow for hardware is notoriously tedious, isn't it?
Tedious is an understatement. You write your code in a text editor on your laptop. You invoke a compiler, which translates that human-readable C code into a monolithic machine code binary.
Right.
Then you physically plug a programmer into the chip, wipe the chip's memory, and flash the new binary over. Then you reboot the chip and observe if the physical hardware behaves the way you want it.
And if it doesn't, like if the LED stays dark?
You have to guess what went wrong, tweak the code on your laptop, recompile, reflash, and reboot.
Right. Compile, flash, pray.
That is the traditional embedded development rhythm, yeah.
But Mecrisp-Stellaris completely subverts this by being fully interactive.
Right. There is no separate compilation step on your laptop at all.
You just flash the tiny 19-kilobyte Mecrisp-Stellaris OS onto the microcontroller one single time.
And from that moment on, the chip is self-hosting.
You connect to it via a simple serial terminal, and you're having a live, direct conversation with the silicon.
So if you type a command into the terminal to turn a physical pin high, the chip parses that text and executes the state change in real time.
And when you want to write a new function, or a word, as they are called in Forth, the compilation happens on the chip itself.
The mechanism behind this is brilliant in its simplicity. Forth relies on a structure called the dictionary.
The dictionary, right?
It's essentially a linked list of words stored in the chip's memory. Each word contains a header with its name, a pointer to the previous word, and then the actual executable machine code, or pointers to other words.
So when you define a new word in the terminal,
Mecrisp-Stellaris instantly allocates memory at the end of the dictionary, compiles your definition into machine code, and updates the linked list.
you are literally teaching the chip new vocabulary in real time.
Yes. And the documentation details this beautifully in a section on the levels of code in Forth programming. It discusses how you build up from the very lowest hardware registers.
Right, because microcontrollers have hundreds of internal switches called registers, which are mapped to specific physical memory addresses.
And Terry advocates for a specific strategy here. Declaring C-style bit fields early in your Forth code to create clean abstraction layers.
Let's unpack that. What exactly is a bit field in this context?
A bit field is a way of masking and manipulating specific bits within a larger memory register. Because normally, you'd have to constantly type out raw hexadecimal memory addresses and do raw binary math in your head to, say, flip the third bit of the register without altering the fourth bit.
Which sounds like a nightmare.
It is. But declaring a bit field lets you map that physical reality to a logical, human-readable name once.
So you define a word like enable clock.
Exactly. And underneath, it is executing the precise bitwise logic on the exact memory address required. You basically build a custom vocabulary perfectly tailored to your physical circuit board.
Now, I can definitely hear some skepticism from a traditional software developer right now.
Oh, I'm sure.
Because C is the industry standard. It runs our cars, our pacemakers, our airplanes. It has decades of mature libraries, static analysis tools, standardized safety protocols.
All very true.
So why on earth would a beginner in the year 2026 decide to learn a radically different stack-based language invented in 1968 to program complex ARM Cortex-M microcontrollers? I mean, isn't that like buying a state-of-the-art sports car and ripping out the steering wheel to install a tiller from a sailboat?
Okay, I see what you're saying, but a better analogy is taking a modern sports car, ripping out the electronic drive-by-wire system, the traction control, and the automatic transmission, and installing a direct mechanical linkage between your foot, the throttle body, and the engine.
Ah, okay.
You lose the safety nets, but you gain pure, unfiltered, instantaneous feedback.
Right, and the power of Forth lies entirely in that feedback loop.
Exactly. Because when you are developing custom hardware, especially the board, you just hand-soldered yourself, things will inherently go wrong.
A pin might have a microscopic solder bridge shorting it to ground.
Or a sensor might have an inverted logic level.
And in C, debugging an unknown hardware failure involves writing complex diagnostic routines, recompiling, flashing, and trying to read the results out of a limited debugger interface.
Which takes forever. But in an interactive Forth environment, you simply type a command to ask the chip, read the voltage state of pin A3 and print it to the terminal.
And the chip replies instantly.
Instantly. You can manually poke and prod the hardware registers live, observing the physical electrical changes on an oscilloscope in real time.
That zero-delay feedback loop must massively accelerate the learning process for a beginner.
It does. It forces you to understand the electrical reality of the hardware rather than just trusting a third-party C library to handle it for you.
And that speed of discovery is exactly what Terry channels into the recommended study path for beginners, right?
Yes.
Which he brilliantly names the Blinky Bazaar.
I love that name.
Because making a single LED blink is the universally acknowledged hello world of embedded systems.
It sounds trivial, but successfully making an LED blink on bare metal proves so many things.
It proves your toolchain works.
Right. It proves your power supply is stable, the chip's internal clock is configured correctly, and the physical output pins are functional.
If you can make it blink, you have conquered the vast majority of the initial friction.
And the documentation doesn't just throw you into writing code either. Step 1 is the Quick Start Guide, which focuses entirely on the mechanics of flashing the initial 19 kilobyte OS onto the bare board.
Which is actually a pretty complex landscape because different chips and development boards support different physical protocols for flashing memory.
Yeah, the guide compares the built-in serial bootloader, ST-Link programmers using SWD, and USB-based DFU-UTL.
So to break down those mechanisms, some chips have a built-in serial bootloader hard-coded into a read-only section of their memory right from the factory, right?
Yes. And by physically pulling a specific pin, usually called BOT0, to a high voltage state while resetting the chip, the processor basically ignores the user flash memory and boots into this factory code.
And that factory code listens on the serial pins for an incoming firmware file.
Exactly. It's an absolute lifesaver for bare chips. But if you have an ST-Link programmer, you can use SWD, which stands for Serial Wire Debug.
Which is an incredibly powerful ARM-specific protocol.
It uses just 2 physical wires, a clock line and a bidirectional data line.
Just 2 wires to do what?
To directly access the memory bus of the microcontroller, bypassing the CPU entirely. It allows you to halt the processor, read arbitrary memory addresses, and flash the OS at incredibly high speeds.
Wow. So Terry really walks the beginner through choosing the right physical weapon to conquer step 1.
He does. And then step 2 is establishing the terminal connection, finding the correct USART pins.
USART. That stands for Universal Synchronous Asynchronous Receiver Transmitter.
Right. It's the dedicated hardware peripheral inside the chip that handles translating the parallel data on the chip's internal bus into a serial stream of bits.
Bits that can be sent over a wire to your computer's USB adapter.
Yes. And once you wire that up and establish this serial connection, you basically have a live chat window open with the silicon.
And that is when you enter the Blinky Bazaar.
The pedagogy of the Blinky Bazaar is just exceptional. It is a sequence of 8 specific tutorials designed for a cheap $10 development board like the F-Zero Discovery.
And by slowly layering complexity onto a single, highly visible physical output, the blinking LED, the learner avoids overwhelming cognitive overload.
Right, because you aren't trying to learn how to initialize an SPI-based OLED display while simultaneously learning stack-based language syntax.
You start with the absolute basics, a simple on-off GPIO toggle.
General-purpose input-output. You write a word that sets the pin high, invokes a crude software delay loop that just counts down from a large number to waste CPU cycles, and then sets the pin low.
It gets the job done, but it monopolizes the processor.
Exactly. So the Bazaar quickly upgrades your skill set to timers. You create a timer-driven PWM fading effect.
PWM being pulse width modulation.
Right. So instead of using a software loop, you configure a dedicated hardware timer peripheral inside the chip.
You set a prescaler to divide the main system clock down to a usable frequency.
And you set an auto-reload register to define the total period of the pulse. Then, by adjusting a capture-compare register, you change the duty cycle, the percentage of time the pin is high versus low within that tiny period.
So the LED turns on and off so incredibly fast that the human eye averages the light output, perceiving it as dimming or brightening.
Yes, and more importantly, you learn to offload work from the CPU to the dedicated hardware peripherals.
From there, the tutorials ramp up to something called the heart blink, which mathematically simulates a beating heart by driving 3 separate LEDs using sine, cosine, and triangle waves.
And keep in mind, we are talking about an ARM Cortex-M0 chip here, which does not have a hardware floating point unit.
Oh, right. So doing complex trigonometry to generate smooth sine waves requires understanding fixed-point integer math and lookup tables.
Which the tutorial walks you through perfectly. It also introduces a makefile build system to manage the growing complexity of the source files.
And it all culminates in a Cortex-M0 assembly language, Blinky.
Because Mecrisp-Stellaris is so transparent, you can drop down directly from the interactive Forth terminal into writing raw ARM assembly instructions, compile them into memory instantly, and execute them.
It totally demystifies the lowest possible level of machine execution.
It does.
But, anyone who has actually sat at a workbench knows that hardware development is inherently hostile.
Oh, absolutely.
A wire is loose, a chip is a dud, a register is locked, or your logic is just flawed. So when a beginner hits a brick wall halfway through the bazaar, what do they do?
Well, Terry provides a dedicated Mecrisp-Stellaris not working diagnostic page that addresses the deep, frustrating gotchas of bare metal development.
What's a prime example of a gotcha?
Processor lockups. When you write standard software on a modern operating system, if you write a bad pointer that tries to access memory it shouldn't, the OS intercepts it, throws a segmentation fault, and gracefully closes your program.
The computer keeps running.
Right. On bare metal, if you write a value to a protected or invalid hardware address, you trigger a hard fault. The processor literally traps itself in an infinite loop of failure.
The entire chip freezes.
The terminal goes dead, the chip stops responding, and panic sets in for a beginner.
I can imagine.
Exactly. The diagnostic page explains the mechanical realities of recovering from this. It also addresses the specific dangers of auto-starting turnkey applications in Forth.
Okay, wait, what's a turnkey application?
You can compile a word and tell Mecrisp-Stellaris, every time this chip gets power, instantly run this word.
Okay.
But if that word contains a fatal logic error or a hard fault, every time you plug the chip in, it instantly crashes before you can even open your terminal to delete the bad code.
So you have built a brick.
You've built a brick. Terry walks you through the precise hardware reset sequences, like holding the physical reset button, asserting the BOT0 pin to bypass user flash, or using an under-reset connection with an ST-link.
To forcefully break the loop, regain control of the core, and wipe the memory.
It's hard-won wisdom from a technician who has bricked countless chips and learned exactly how to unbrick them.
Which highlights a really fascinating juxtaposition in this whole ecosystem.
What's that?
Forth is undeniably a vintage language, right? Rooted in the punch card and teletype era of the late 1960s.
Yeah,
But the developer workflow Terry Porter advocates for is cutting edge.
it really is.
He is actively modernizing a vintage toolset, completely destroying the myth that embedded programming requires downloading massive, clunky, proprietary vendor IDEs that take 10 minutes to load and hide the build process behind graphical buttons.
And the first essential tool in his modern workflow is the serial terminal, and the configuration here is deeply intentional.
He recommends GNU Screen, but specifically configured for a blazing fast 480,600 baud rate.
Right. Most standard Arduino tutorials start a beginner at 9,600 baud.
So to explain the mechanism, baud rate dictates how many symbols per second are transmitted across the serial wire.
Because UART communication requires framing, adding a start bit, parity bits, and stop bits around every byte of actual data, a 9,600 baud rate translates to moving roughly 1 kilobyte of data per second.
And when you were developing interactively in Forth, you aren't just typing single lines.
No, you are frequently sending entire source code files down the serial line to be compiled into the chip's dictionary live.
And at 9,600 baud, sending a complex library feels like watching paint dry.
It completely disrupts the flow state of programming. But at 480,600 baud, the transmission is effectively instantaneous.
But physics gets in the way at 500,000 baud, doesn't it?
It does. If the computer shows text down the wire faster than the tiny microcontroller can parse the text, allocate memory, and compile the machine code, the chip's internal serial buffer will overflow.
Data will be lost.
And the compilation will fail with bizarre syntax errors.
Right, so to solve this, the documentation insists on using hardware handshaking, specifically RTS and CTS.
RTS stands for Request to Send, and CTS is Clear to Send.
So instead of relying solely on the two data wires, Hardware handshaking utilizes additional physical wires between the USB adapter and the microcontroller.
Right. If the chip's buffer is getting dangerously full while it processes a complex fourth definition, it physically toggles the voltage on the CTS line.
The computer's hardware sees that voltage change and instantly pauses the data stream for a fraction of a millisecond until the chip toggles the line back, signaling it is ready for more.
It ensures flawless high-speed data transmission without corruption.
It's raw mechanical flow control.
And pairing with that high-speed terminal is the actual text editor. Terry doesn't use Notepad or some bloated IDE. He uses the Helix editor.
Helix is a modern modal text editor built in Rust, heavily focused on keyboard-driven navigation and extreme efficiency. But the real game changer is how it integrates with language servers.
Language server protocols, or LSPs, have revolutionized modern software development. But seeing one applied to a 1968 language is a massive leap forward.
How did it work traditionally?
Well, traditionally, if you wanted auto-completion or inline documentation in an editor, the editor's developers had to write custom parsing engines for every single programming language.
That sounds inefficient.
Very. The LSP architecture standardizes this. The text editor acts as a generic client. In the background, a language server, a separate program specifically built for Mecrisp-Stellaris, runs and analyzes your Forth code in real time, building an abstract syntax tree.
And the editor and the server communicate via JSON RPC.
Exactly.
Meaning you are writing code in a minimalist bare metal language, but as you type a hardware register name, the editor asks the language server for context, and a hover box instantly appears showing you the exact documentation for that register before you even finish typing.
You get the raw, unabstracted power of bare metal Forth, wrapped in the ergonomic luxury of a 2026 developer environment.
It's like putting a state-of-the-art GPS and digital fuel injection system into a classic 1960s muscle car. It's raw, direct power, but with modern navigation.
That is exactly what it's like. Terry even customized the Mecrisp-Stellaris kernel itself to improve this workflow.
Oh, right. He implemented a carriage return to line feed or CR to LF conversion modification.
Yes. In serial communication, parsing text lines and tracking errors can be messy, depending on how your terminal handles hidden ASCII line-ending characters.
Because when a syntax error occurred during a fast file transfer, standard Forth would halt, but tracing exactly which line in your massive source file caused the error was tedious.
By modifying the kernel's text parsing buffer to explicitly manage these line endings, Terry created a system that halts and perfectly identifies the source code error location, seamlessly integrating with the modern editor's diagnostic tools.
It's a perfect synergy of old and new, and that synergy is absolutely necessary when we confront the reality of modern silicon, because the hardware has evolved into a state of absurd complexity.
It really has. We touched on bit fields earlier, the individual logical switches inside the chip's memory registers. The documentation highlights a stark comparison regarding the explosion of these registers over the last decade.
It is the single biggest bottleneck in bare metal programming today.
It is. The documentation compares an older, simpler chip, the Texas Instruments MSP430G2553, which has 17 hardware peripherals, 113 registers, and 503 distinct bit fields.
Okay.
A programmer could reasonably sit down with a PDF datasheet for that chip, read through it, and manually type out the memory addresses for the 500 switches they might need to use.
But then you look at a modern high-end ARM Cortex M7 chip, like the STM32S746.
Right.
It features 98 complex peripherals, 1,778 registers, and a staggering 14,338 individual bit fields.
And if you are adhering to the bare metal philosophy of mapping the hardware directly in your code, manually typing out the hexadecimal memory addresses and calculating the bitwise shifting masks for 14,000 distinct features is practically impossible.
A single typo in a hex address could result in weeks of agonizing debugging, because writing to the wrong configuration register might subtly alter the timing of a peripheral without throwing an obvious error.
The manual transcription of datasheets simply does not scale to modern silicon.
So how do you solve that?
The semiconductor industry relies on a standard called CMSIS SVD, which stands for Cortex Microcontroller Software Interface Standard System View Description.
It's a massive, highly structured XML file provided by the chip manufacturer.
Yes. This XML file exhaustively details the entire memory map of the chip. It contains nested tags defining every peripheral's base address, every register's offset address within that peripheral, and the exact bit position and width of every single field.
It's the manufacturer's definitive digital map of the silicon. But an XML file isn't executable code.
Right.
So Terry's documentation introduces a custom tool called SVD2 I was looking at the mechanics of this tool, and it is a brilliant piece of automation.
It really is. It parses the manufacturer's XML schema and automatically generates a massive file of pure, perfectly accurate Forth source code.
So instead of a human calculating that the clock enable bit is at offset 0 by 30 from the peripheral base address of 0 by 40,021,000,
SVD2 of Forth reads the XML, performs the arithmetic, and emits a fourth word that pushes that exact calculated memory address to the stack, complete with the manufacturer's descriptive name.
So in a matter of seconds, a single developer can generate a comprehensive, bug-free vocabulary for a massively complex Cortex M7 chip.
Exactly.
But this raises a philosophical question about the bare metal ethos, right?
I was listening.
The entire premise of using Forth and abandoning bloated C libraries is radical transparency. You are supposed to understand the hardware completely.
Right.
If you are relying on an automated script to generate 14,000 lines of hardware definitions for you, aren't you just building another black box? I mean, how is the SVD2 Forth any different than relying on a heavy hardware abstraction layer library from the manufacturer?
It comes down to the fundamental difference between an abstraction that hides mechanism and an automation that reveals mechanism.
Okay, break that down for me.
A black box C library hides the actual memory addresses behind compiled binary functions. You don't know what the function is doing internally unless you spend hours reverse engineering the source code.
Right.
SVD2 Forth is fundamentally different because it generates transparent, human-readable Forth source code.
Ah, so it isn't a compiled library you are blindly trusting. It outputs raw text files.
Yes. You can open the generated file in Helix, search for the enable clock word, and look at the exact hexadecimal memory address and bit mask the script calculated.
It automates the tedious transcription, but it leaves the mechanism completely visible. It's zero-cost abstraction.
Exactly. It allows the minimalist philosophy of Forth to scale to massively complex architectures without sacrificing the transparency that makes bare metal programming so powerful.
And that transparency becomes critically important when you realize that the physical hardware you were trying to program might actually be lying to you.
Oh, yes. Which brings us to the harsh realities of the modern hardware supply chain.
Yeah, the documentation doesn't just teach code, it teaches street smarts. It specifically tracks a timeline of chip supply times stretching from 2017 through September 2022, capturing the era of the global semiconductor shortage.
And during that window, buying a genuine STM32 microcontroller from official distributors was nearly impossible.
Fabs were at capacity, automotive companies were halting production lines, and lead times for tiny silicon chips stretched into years.
Nature abhors a vacuum, and the gray market responded. E-commerce platforms like AliExpress were absolutely flooded with clone, counterfeit, and gray market STM32 chips.
For a hobbyist or an electronics technician trying to build a reliable project, this was a nightmare.
A total nightmare. A counterfeit chip might look identical on the outside, wrapped in the same black epoxy and laser etched with the STMicroelectronics logo, but the silicon die inside could be completely different.
And clones often fail under high thermal loads, lack specific advanced peripherals, or have subtle flaws in how their memory controllers operate.
Right. If your code relies on highly specific, bare metal register timings, a clone chip that takes one extra clock cycle to access flash memory will completely break your program.
Terry's response to this chaos wasn't to throw his hands up. He built a software polygraph test.
Yes, the documentation details the Blue Pill Diagnostics V1.6 tool, specifically designed to interrogate the wildly popular and heavily counterfeited STM32 F103 Blue Pill development boards.
And the diagnostic process is a masterclass in utilizing low-level access.
First, it queries the standard identification registers. Every ARM Cortex chip has a CoreSight debug access port containing an ID code register, and chips usually have JTAG manufacturer codes burned into ROM.
But sophisticated counterfeiters quickly learned to simply fake those static ID codes. The silicon would lie when asked who made it.
So Terry had to go deeper than the ID tags. The tool actually utilizes a built-in machine code disassembler.
Because Mecrisp-Stellaris operates directly on the hardware, the diagnostic tool can systematically read the peripheral configurations, the memory sizes, and execute highly specific instruction sequences to profile the actual execution timing.
Yes. Different silicon foundries like CKS or GigaDevice, who produce popular clones, have subtly different physical pipeline architectures or flash memory prefetch buffers.
So by stress testing the physical execution physics of the chip and comparing the results against known STMicroelectronics baselines, The tool forces the silicon to reveal its true identity, regardless of what the laser-etched label says.
You are literally profiling the physical silicon.
And during these interrogations, Terry's tool unearthed a massive, fascinating hardware secret, the 128 kilobyte flash memory variant phenomenon.
This is wild. You could buy a genuine STM32 chip that was explicitly sold, marketed, and laser labeled as having 64 kilobytes of flash memory.
Right?
But when the diagnostic tool probed the upper boundaries of the memory map, it would discover a fully functional, pristine extra 64 kilobytes of memory hiding in the dark.
The chip actually had 128 kilobytes.
It seems counterintuitive, right? Why would a manufacturer give you double the memory for free and lie about it on the packaging?
The answer lies in the intense economics of silicon wafer fabrication.
Establishing a production line for a microscopic silicon die costs millions of dollars. It is incredibly expensive to maintain separate assembly lines for a 64 kilobyte die and a 128 kilobyte die.
So they use a process called binning.
Precisely. The fab runs one single massive production line, pumping out millions of 128 kilobyte chips.
And when a customer order comes in for the cheapo 64 kilobyte variant, it is vastly more cost-effective for the manufacturer to simply take a fully functional 128 kilobyte chip, laser etch the 64 kilobyte label on the plastic, and ship it.
The extra physical memory is sitting right there on the silicon, completely functional. The manufacturer just doesn't legally guarantee it.
But if you are using a standard C library provided by the manufacturer, that software layer restricts you to the official 64 kilobyte boundary. The abstraction enforces the label.
Yes. But because Mecrisp-Stellaris allows you to interactively explore the raw memory space, address by address, you bypass the abstraction entirely, discover the hidden territory, and can confidently deploy code into it.
It is the ultimate vindication of the bare metal philosophy. You are no longer artificially constrained by a manufacturer's marketing department.
And that fierce independence, the desire to unearth the truth, strip away artificial constraints, and share those discoveries, feeds directly into the broader cultural context of this deep dive.
Because the documentation isn't just a technical manual, it is a manifestation of the Forth community's philosophy.
And that philosophy has some deep historical friction embedded within it.
Yeah, reading through the material, it is clear this community isn't a unified utopia. There is a deeply rooted tension regarding standardization, specifically highlighted in a section provocatively titled ANSI Forth is Anti-Forth.
We definitely need to unpack that argument because it fundamentally shapes how developers like Terry build their tools.
So the argument traces back to Charles Moore, the original inventor of Forth, right?
Yes. His philosophy was that the language shouldn't be a rigid, immovable structure. Instead, Forth should be a highly individualized extension of the specific hardware it runs on, tailored by the programmer to solve one specific problem with maximum efficiency.
But in the 1990s, as the software industry industrialized, there was a heavy push for standardization, leading to the ANSI Forth standard.
The goal was portability, the ability to write code on a desktop PC and easily compile it on an embedded controller, much like the ANSIC standard allows.
Which sounds entirely logical if you want corporate adoption and a massive ecosystem of interchangeable software libraries.
True. But prominent purists in the community, including Charles Moore and figures like Garth Wilson, who were heavily quoted in the documentation, argued that standardization destroyed the very essence of the language.
They argued that by forcing Forth to conform to a universal lowest common denominator standard, the language became bloated with unnecessary compliance features.
It lost its ability to tightly hug the unique, specific quirks of the target hardware. If you standardize the language, you abstract the machine.
Thus the battle cry. ANSI Forth is anti-Forth.
It is a fundamental clash between the desire for frictionless portability and the pursuit of absolute uncompromised performance and customization.
And that philosophy of radical independence heavily influenced how Terry Porter manages this massive 100-page living documentation project today.
He didn't just upload his Markdown files to GitHub and call it a day, which is the default workflow for 99% of open source projects in 2026.
Right. He actively transitioned the entire ecosystem away from centralized platforms and adopted the Fossil Distributed Version Control System.
Fossil DVCS is a fascinating piece of technology that perfectly mirrors the minimalist, self-contained ethos of bare metal programming.
Most developers use Git to track changes in their source code.
Git is phenomenal at managing text files, but it is strictly a version control tool. If a project wants a wiki for documentation, a ticketing system for bug tracking, or a web interface to view the code history, the developer is forced to rely on a massive, centralized third-party platform like Microsoft-owned GitHub or GitLab.
You are outsourcing your project's infrastructure to a corporate cloud.
Fossil takes a radically different architectural approach. Fossil integrates the cryptographic version control for the source code, the entire wiki, the bug tracking system, forum threads, flowcharts, and a built-in web server engine into one single, standalone SQLite database file.
So when you want to clone the Mecrisp-Stellaris documentation project, you don't need to maintain a continuous connection to a cloud server.
You download the tiny Fossil executable and the single project database file.
In that one file, you possess the complete cryptographic historical universe of the project.
You can run the web server locally on your laptop, browse the wiki, and review code commits while completely offline. It is entirely decentralized and self-sovereign.
And the mechanism for community collaboration in this decentralized model is completely distinct from the standard GitHub pull request workflow.
Yes, if a reader works through the Blinky Bazaar, finds a typo in the timer configuration tutorial, and wants to fix it, they make the edit in their local Fossil repository.
Fossil then generates a cryptographic bundle, a compressed snapshot of just their specific changes mathematically linked to the project's history graph.
The user can literally just attach that small bundle file to a standard email and send it to Terry. Terry receives the email, reviews the bundle offline, and merges the changes into the master database.
The infrastructure is incredibly resilient. If GitHub goes down or changes its terms of service or blocks a region, the Mecrisp-Stellaris project is completely unaffected.
The community owns its tools and its data, which brings us to the cultural cornerstone highlighted in the documentation. The first rule of Forth: don't hide your tools.
When you belong to a community that expects radical transparency, it fundamentally changes how you structure your code and your projects.
When Terry built the Blue Pill Diagnostic Suite, or SVD2 Forth, he didn't compile them into closed binaries, obfuscate the source, and charge a licensing fee.
He published the bare source code and explained the methodology, empowering the next developer to understand, modify, and improve the tool for their own unique hardware scenario.
It forces a culture of modularity and clarity. You aren't just writing a script to make an LED blink. You are writing a tool to calculate the exact hardware timer frequency limits, and you are sharing that mathematical tool with the community.
It is a holistic approach to technology. Every layer, from the physical soldering of the silicon to the cryptographic tracking of the documentation, is visible, transparent, and controllable by the individual.
Absolutely.
So let's synthesize this incredible journey. We started with the mission of mapping a path for an absolute beginner to break into the black box of bare metal computing.
And the documentation provides exactly that.
The path starts with grabbing a cheap Cortex-M development board and approaching it with the mindset of an electronics technician studying the physical schematics, understanding the voltage levels, and acknowledging the reality of the physical pins before writing a single line of software.
You ditch the massive, opaque C compilers and install Mecrisp-Stellaris, establishing a 19 kilobyte, hyper-efficient, fully interactive conversation directly with the silicon.
You set up a modern, uncompromising workflow using a high-speed JNU screen terminal with hardware handshaking and a blazing fast Helix editor empowered by a language server protocol, proving that vintage, bare metal languages don't require sacrificing modern developer ergonomics.
You step deliberately through the Blinky Bazaar, systematically conquering the hardware peripherals from simple GPIO toggles to complex, math-driven PWM timers and raw assembly execution building complexity, one verifiable physical output at a time.
You leverage powerful automation tools like SVD2 Forth to translate massive manufacturer XML databases into transparent human-readable code, allowing you to tame chips with tens of thousands of registers without losing your mind or your bare metal transparency.
You deploy low-level diagnostic tools to interrogate your hardware, mapping the physical execution pipeline to catch counterfeits and unearth hidden memory banks that the standard software abstractions would have kept hidden from you.
And you engage with a community that prioritizes extreme independence, utilizing decentralized tools like Fossil DVCS to ensure your knowledge base remains entirely under your control, while adhering to a philosophy of relentlessly sharing your tools.
It is an intensely empowering process.
And I want to emphasize why this matters, why you, the listener, should care about this journey, even if you decide you will never hand solder a microscopic QFN chip in your life, even if you never type a single stack-based Forth command.
It's about a shift in perspective.
Yes. Understanding this bare metal interactive methodology does something profound to your perspective on technology. It forcefully strips away the illusion of magic in modern computing.
It replaces the passive anxiety of dealing with impenetrable black boxes with the active empowerment of true comprehension.
You realize that a computer at its core is not magic. It is just millions of microscopic physical switches. And if you learn how to talk to them directly, you can command them to do exactly what you want without compromise.
By understanding the foundations, you reclaim a sense of ownership over the technology that permeates our lives. You transition from being a passive consumer reliant on corporate abstractions to an active director of the physical hardware. You understand the trade-offs being made in the layers above.
Which brings us right back to the beginning of this deep dive. We talked about taking a crowbar and prying the lid off the black box. And I want to leave you with a final lingering thought to chew on today.
What is that final thought?
Think about that 60-cent bare microchip we discussed at the very start.
Yeah.
A physical sliver of silicon, practically the size of a speck of dust, running an entire operating system that occupies a mere 19 kilobytes of memory.
It's incredible.
A system fully capable of parsing text, compiling machine code in real time, performing complex mathematical trigonometry, managing interrupt-driven hardware timers, and executing multitasking routines with deterministic microsecond precision.
All in 19 kilobytes.
Right. If a single hobbyist sitting at a messy workbench with a soldering iron and a 60-cent chip can squeeze that level of sheer functional brilliance out of just 19 kilobytes of software, what does that say about the gigabytes of bloated, sluggish, resource-hungry software that we simply accept as necessary on our everyday laptops and smartphones?
That's a very good question.
Are we actually innovating with our modern software stacks, or are we just using infinite layers of abstraction to hide our own inefficiency?
It really forces you to question how much raw performance and capability we are continuously leaving on the table just for the sake of developer convenience.
It does. It makes you realize that maybe the true magic isn't found in the massive, opaque software layers we pile on top of the hardware. Maybe the real magic is what the bare metal is actually capable of once you finally decide to talk to it directly.